Welcome to the Explainer. We're about to dive into something that can look pretty scary at first, but is actually one of the most powerful things in your math toolkit: trigonometric identities. Think of them as a secret code that helps you simplify really complex problems. Let's get into it.
So, right off the bat, I'm going to throw this at you. Take a look. It looks like a total mess, doesn't it? Well, believe it or not, by the end of this, we're going to untangle this whole thing and find a ridiculously simple answer. But first, we need to know the rules of the game. So, what in the world is an identity? Well, at its heart, it's just a statement that's always true. It's an equation that works for any valid number you plug in. It's not something you solve, it's a fundamental rule you can always count on. I love this quote because it puts it in really practical terms. Think of identities as different names for the same thing. They tell us that two expressions that look totally different are actually identical. And that means we can swap them out anytime we want to make our lives easier. And that's exactly what we're going to do right now. We're going to build our very own trigonometric identity toolbox. We're going to stock it up with the most important identities. These are the tools you're going to use again and again to break down complicated stuff into something way more manageable. All right, first tool for the toolbox, the reciprocal identities. These are the most basic ones, and they just connect each trig function to its mathematical flip side. And you can see how they pair up. Sine is just 1 over cosecant. Cosine is 1 over secant. Tangent is 1 over cotangent. And of course, it works the other way around too. It's a simple idea, but it's super powerful when you start rearranging things. Okay, next up, let's add the quotient identities to our kit. These are really cool because they show us how the functions are all related to each other. Specifically, how we can define tangent and cotangent in a whole new way. Now, this right here is a huge one. Tangent is simply sine divided by cosine. And since cotangent is just its reciprocal, it's cosine divided by sine. Honestly, this is a game-changing strategy. A lot of the time, when you're stuck on a problem, the best first move is to turn everything into sines and cosines. Our third set of tools is all about dealing with those pesky negative signs inside the function. The odd and even identities give us a clear rule for how every trig function behaves when you feed it a negative angle. And there's a really simple pattern here. The only even functions are cosine and its reciprocal, secant. For them, the negative sign inside just vanishes. For all the other odd functions, you can basically just pull the negative sign right out front. And for our last set of essential tools, we have the co-function identities. These are the ones that connect a function to its co-buddy. So sine connects to cosine. Tangent connects to cotangent. You get the idea. What these are really telling you is something about the graphs of these functions. A sine wave is literally just a cosine wave that's been shifted over a little bit. So these rules are just a neat algebraic way of describing that visual relationship. Okay, our toolbox is officially packed. We've got reciprocals, quotients, the odd/even rules, and co-functions. So, remember that monster of a problem from the beginning? Let's go back and absolutely crush it with our new tools. All right, let's break this down. On top, we've got cos of pi over 2 minus x. We just learned that our co-function tool lets us swap that for sine of x. Simple. On the bottom, we have cos of negative x. Our even identity tool says we can just get rid of that negative, so it becomes cos of x. And finally, tangent of x. We'll use our quotient tool to rewrite that as sine of x over cos of x. Now we just plug all those simpler pieces back in. So when you substitute everything back in, the top becomes sine x times sine x. The bottom becomes cos x times sine x over cos x. Well, the cosines on the bottom cancel out. Then one of the signs on top cancels with the one on the bottom, and the whole entire mess just simplifies to sine x. How cool is that? And this is why it matters. This kind of simplification is used all the time in physics to understand complex waves. Okay, so these tools are amazing for cleaning up messy fractions, but that's not all they're good for. They can also give us these really elegant shortcuts to find values without even touching a calculator. Check this out. If I tell you that cosine of some angle x is 0.75, and then I ask you for sine of pi over 2 minus x, you don't need to find the angle. You just have to recognize the pattern. You grab your cofunction tool, which tells you that sine of pi over 2 minus x is identical to cosine of x. So, the answer is just 0.75. Done. All right, now for what I like to call the final boss level of using identities, actually proving them. This is where you're not just finding an answer, you're showing, step by step, how two things that look completely different are actually the exact same thing. Now, there is one golden rule here, and you cannot break it. You have to pick one side of the equation, usually the messier looking one, and work only with that side. The goal is to use your tools to transform it until it looks exactly like the other side. So let's try one. Here's our mission. Prove that tan x plus cot x is the exact same thing as secant x times cosecant x. We're going to start with the left side, and our destination is the right side. So here's our game plan. First, we'll use that classic move, convert everything to sines and cosines. Then we'll do some algebra to get a common denominator. Now at that point, we'll need a new tool, one of the most famous of all, the Pythagorean identity, which says that sine squared of x plus cosine squared of x is always equal to 1. Once we use that, we can simplify and use our reciprocal tools to get to the finish line. And that's really the whole point here. Identities aren't just random formulas you have to memorize for a test. They are the actual grammar of trigonometry. They're the rules that let us translate and transform the very language we use to describe some of the most important things in our world, like circles and waves and vibrations. Which brings us to a final thought for you to chew on. We've talked about odd and even identities with all this algebra, but what do they actually look like? How could you just glance at a graph of a function and know instantly if it's odd or even? Think about symmetry. What kind of symmetry would an even function have, and what about an odd one? I'll leave you with that. Thanks for watching.